Hi everyone, I'm Pengjian Wu. Many thanks for having a chance to introduce my recent work suppressing GRS disturbances with TDI combination. And as we all know, in 2015, the first detection of the gravitational wave were made by the Van LIGO and Virgo, and it opened a new era of the gravitational wave astronomy in order to exploring the exciting sources in the lower frequency band from 0.1 million hertz to 0.1 hertz. People are trying to put a laser interferometer in space. The best known mission is LISA, and also the Chinese mission Taiji and Tianjin focus on the same scientific objective. And generally, the expected gravitational wave signal of the spaceborne mission lasts for a long time, maybe lasting for a month or for years. So if you want to measure the related parameter, continuous measurement without disruption in the data stream are normally required. It means that we have to try our best to stay in a good condition, such as no data gap, long-term stabilize, no disruption, normal requirement. And here's the brief introduction of the Taiji mission, and it's the roadmap toward the Taiji mission. The first step is develop and test the Taiji key technology in the ground laboratory. And here's the Taiji-1 satellite, which has been launched in the 2019 and test the key technology such as interferometer, the gravitational reference sensor, which we also call the GRS. Actually, the Taiji-1 is the first day of the Taiji mission. In the next step, we eventually launched the Taiji-2, which also called the Taiji Pathfinder. Finally, Taiji-3 will go into space around 2030s and listen to the gravitational wave signal. And thought people launch LISA Pathfinder and Taiji-1 is still foreseeable disruption in science measurement. It will come from the schedule maintenance or the unexpected instrument anomalies. Here we show some anomalies in the mission which carry the GRS or the accelerometer system. This one is the glitches in the LISA Pathfinder, and this one is the disturbances in Taiji-1 satellite, and this one is the twang in the GRS, and this one is the glitches in the GFO. Those anomalies are not only appear in their payload, but in the future, in the LISA and Taiji mission, those noise has also in the final science measurement. It seriously affects the continuity of the data, so we have to find some way out to deal with those anomalies. If we want to know how those anomalies affect in science measurement, first of all, we should understand the measurement logic. Here we introduce the split interferometer for LISA and Taiji mission, using the equation in this slide, and here's the science measurement, and here's the testament interferometry measurement, and here's the reference interferometry measurement. And why we give more attention in the GRS system? Because the GRS is the key payload in the LISA and Taiji mission. The test mass in the GRS system serves as the air mirror of the interferometer, and at the same time, it's the fragile. The residual precision noise directly affects the sensitivity of the mission. Here you could see the influence factor of the dynamic of the test mass. And from the experiments of the LISA Pathfinder, it has the long glitches and the short glitches. For the long glitches, it lasts for 3 months, maybe longer. And for the study of the LISA Pathfinder team, the only credible explanation that seems to match most of the long glitches is outgassing. In GRS, there are also a twang in accelerometer system, which caused by the heater switches. And this picture shows how the GRS respond to the thruster in Taiji-1. And these two show the period signal in time series and in ASD, which produced by the reaction wheel. And from the experience of those missions, the performance of the GRS for LISA and Taiji mission may be affected by unexpected anomalies and schedule maintenance. Those glitches or long-term disturbances will be picked up by the testament interferometer, not the science interferometer. And at the same time, those noise cannot cancel out in TDI. And if those anomalies happens, it will be a disaster in science data analysis. And according to the LISA Pathfinder and Taiji-1, I model the glitches and long-term disturbances. And those two models could meet the requirements for testing my new method in this talk. And the glitches produce the sensitivity curve in the low frequency bands. Here we compare the testament interferometry output with actual glitches, the orange curve, and the test map interferometer without anomalies, the blue curve. And in my simulation, disturbance lasts for 10 hours and it's totally destroyed the measurement. And you can see from the SD, and if the long-term disturbance happen, it will be a disaster. So we simulate the actual noise and add them into the test map interferometer measurement of the satellite 2 here, and we find in some special TDI combination, the actual GRS noise in the satellite 2 has almost the same time delay. So for canceling, we suggest a new channel P here, which could suppress the position noise. And for testing our new method, we use our simulator. This simulator is developed by myself. And in this simulator, I generate the data set with the glitches and long-term disturbances and science measurement, reference measurement, and so on. And here's the principle of the channel P. The key point of the channel P is the arm length difference between two combinations of the same noise term is almost the same. For simplified, we chose the first generation TDI for this question. And this equation is the alpha combination and gamma combination. The letter D here is the delay operator. And in the first generation, D1 prime is the same as the D1. And here is their photon path. The photon path of the alpha is start from the satellite 1, and the gamma is start from the satellite 3. You could see that the actual noise term will be remains in the combination, and the corresponding actual noise term has almost the same time delay. And for example, the lower delta 2 here in alpha will delay twice. One is the D1 and one is the D2. And the lower delta 2 in gamma and also delay twice. One is D2 and one is D3. So the difference of the delay time of the same noise term delta 2 here between these two combinations come from the difference between D3 and D1. So according to the optimal orbit of the LISA and Taiji, arm length difference is less than 24,000 kilometers. And compared with the previous of the expected gravitational wave signal, the delay difference is about 0.08 seconds, and it's rather small. It means that the difference of the actual noise in above equation will be significantly suppress the noise component with correlation time longer than a few seconds. So if we could combine the alpha and gamma further and get the channel P. And here's the P2, hence the P1 and P3. And here's the channel P for the N generation TDI. And in the Fourier domain, we could see the difference between two arm length difference. The smaller the arm length difference, the smaller the suppression factor, which also means that we could get a better result in a small arm length difference. The suppression factor here, the suppression factor for the N generation case, and without knowing the detail of the noise, channel P has ability to suppress the actual GRS noise. And here is my simulation of my new methods. First of all, considering a static model, we set the constant arm length and we simulate the laser frequency noise, optical bench displacement, short noise, GRS, glitches, disturbances. And we found that the TDI output will totally dominate by the worst GRS noise. But we combine alpha and gamma further, and we got channel P. In our expectation, the channel P could successfully suppress the anomalies, including the glitches or the disturbances and the disturbances. The orange curve, which represents the channel P, consists with the green curve, which is the TDI output without anomalies. And then considering the moving model, we include the orbit data, and the result is the same as those in static model. Again, the orange curve, which represents the channel P, consists with the green curve, which is the TDI output without anomalies. Also, we're considering a special case with only GRS noise, and we found the results totally agrees with analytical results. And here is the conclusion of my talk. without the need for the detailed noise model. Such TDI channel P could successfully suppress the position noise from the GRS at the same satellite. And with analyze and numerical simulation, we have proved the GRS position noise suppression factor could reach 10 to the -5 to 10 to the -3 in the sensitive bands. And the channel P could successfully suppress the actual GRS noise, and at the same time, it remained the expected sensitivity level for the data. And with this approach, the visibility of the data and Taiji mission could be improved, and the risk related to the GRS system could be significantly reduced. Many thanks for listening, and any question about this talk could email me or leave your question below this video. Thank you.